Okay, this is going to be a relatively quick review of the network model, or actually network models that you should have learned in 160 or 161. So the first one, and the one we probably deal with the most often, is the OSI model. The standard for that was published in 1986 by ISO, and as hopefully you recall, it's a 7-layer model. The other model that we deal with on occasion is the TCP IP model, and wanted to tell a little story related to that. Back in, I think, the early 90s, there was a company called Next Computer, and Next Computer is what Steve Jobs did in approximately the 10-year period that he was not with Apple. And UK was one of the largest installs of Next Computers in North America, and I went to developer camp for a week, which was a very intensive programming class. So we went in Monday morning, started bright and early at 8 o'clock, just jumped into programming and learning the programming paradigm for the Next Computers. And then around 10 or 10:30, we went into a conference room and had a break. And our instructor said, let's go around the table, tell me your name, who you work for, and why you're here. So mine was something like, I'm Wayne Beach, I work at the University of Kentucky. I'm here to learn about programming the next systems so that I can help our faculty members develop apps. So we go around the table, and towards the end there's a guy who says, my name is Bob Metcalf, I'm retired, and I'm here to see, what this next thing is that Steve Jobs is doing. And everybody laughed. So a little later we were talking to him, and he's like, retired? And he says, well, that sounds so much better than unemployed. And my lab partner, Dan Lavin, who was editor of Next World magazine, pointed at Bob, who was sitting in front of us, and he's like, who's Bob? And I'm like, I don't know, his name sounds really familiar. So at lunch, he went back to his hotel room, and they actually published a book called Who's Who in Computing, or Who's Who on the Internet. And he came back from lunch and kind of leaned over and elbowed me and goes, Bob invented Ethernet. So I was actually in Next Developer Camp with Bob Metcalf. And like I just said, he created TCP/IP in the 70s. It was adopted as a standard in 1983. And this is kind of a sketch pretty close to the famous napkin where he invented Ethernet. And notice towards the bottom that they said the cable that is shown is listed as, quote, the ether. And what the ether came from is long time ago, scientists had trouble explaining how sound traveled from somebody to another person's ear. And they basically said there was something in the air called the ether, and that the signals or the voice traveled over the ether. So he used that and created what's referred to as Ethernet. And notice it shows here, kind of towards the top of that image, basically your NIC, your network interface card, and how it connects to the network. So that was his first concept of what Ethernet was. We said that the OSI model had 7 layers. Here they are. You should be familiar with this. If not, you need to refresh your memory, including the name of the layers and their protocol data units. If you had me for 161, you've heard this before, but there are a couple of mnemonic devices to help you try to get these layers in the correct order. and if from bottom up, the first letter, basically you think of please do not throw sausage pizza away. And that gives you the first letter of each of those words, gives you the first letter of the layer name. If you're going from top down, the mnemonic is all people seem to need data processing. And of course, data processing is a really old term that's probably not used anymore. I always do the please do not throw sausage pizza away, and then from that get the layer, and then based on the layer, give the PDU. For the TCP/IP model, it's a 4-layer model, as we said. These are the 4 layers. They're drawn like this because the physical layer in the TCP/IP model correlates to the first 2 layers of the OSI model, and up at the top, where they just have the all-encompassing application layer, that matches up with what's called the upper layers, layers 5, 6, and 7 in the OSI model. And here I have a slide that kind of shows you that. You should be able, giving an empty chart like this, for either the OSI model and or the TCP/IP model, be able to fill out all the information that is shown here. You will probably have to do that on your midterm exam. You'll probably have homework where you have to do that. Now in 160 or 161, you should have talked about the reasons for layered network models. The first is it assists in protocol design. That is, when you're designing things, it lets you concentrate on a part or a layer and deal with the protocols and the functionality at that layer without worrying about the whole thing. That's why I tell my 120 students when I teach 120 is you shouldn't try to think about the problem as a huge whole. You should kind of break it into pieces and work on the pieces. The other thing by having a standard or a protocol standard is it fosters competition. If you say how something should work and provide that to people, they should be able to create equipment or computers or devices that can work on the network. That's why you can take pretty much any piece of equipment that was designed to work on an Ethernet network, just plug it in and it works. The other thing it does is it kind of gives you some common language or common terminology that you can use to talk about networking with other people. The other thing is if you break it into layers and talk about it, if you break one layer or introduce a problem in one layer, it does not affect the other layers. So what we're going to do now is go back and kind of layer by layer talk about some things that hopefully are a review that you should know about each of these, and we'll start at the bottom at layer 1, which is the physical layer. Again, the picture we had before said that the PDU is the bit. Its purpose is to represent bits and transfer or transmit them from a source to a destination. And at that layer, when we talk about kind of physical things, we're talking about the media, which we'll talk about here shortly in more detail, and their devices. So by the time you hear this lecture, you will have hopefully watched my lecture on additional networking equipment. And in that, we talked about repeaters and hubs. Those are layer 1 devices. Now, this is how we would like to think about bits traveling. And that is, we either have a 0 voltage or some high voltage, often 5, that represents a 1. So this is how we think about bits traveling over the network. This signal shown at the bottom is referred to as a non-return to 0 signaling. If you notice the 4th and 5th bits, they're both 1s. I just stayed at high voltage and a high voltage. I never transitioned back down to a 0 during those bit periods. We have 3 types of media that are the most common. The first is copper. It is represented as an electrical signal on a wire. Notice this looks real jagged. Has to do with the transitions from 1 to 0 and how those are transmitted on the wire. This looks nothing like what we had on the previous side, where we said this is what we like to think that it looks like on the wire. This is what it actually looks like. Another type of media we have is fiber optic cable, and fiber optic cable is going to represent the signal as pulses of light. So this is representing the different colors we might have. Excuse me. We have wireless networking. Cisco likes to call it wireless media. Well, the media is really the air or the free space around you. So there are different types of signals you can send. The AM is amplitude modulation. So notice that the peaks, the highest point and lowest point on the signal going over the wire is smaller for a 0 and a higher voltage or highest peak and valley for 1s. So that's varying the amplitude of a sine wave that is traveling across the media. The next way is called frequency modulation. A 0 is a lower frequency than a 1. And this is the way, you know, if anybody still has a radio in their car, AM and FM bands of your radio. And then finally, the last way is called phase modulation. And these sine waves that are shown for a 0 and a 1 are 180 degrees out of phase. So you'll notice the first one starts up for a 0. For the 1 bit, the first part of the sine wave starts down. So that's phase modulation. There are different types of things called signaling that we can have. A very popular one is Manchester coding, and basically we represent a 0 from a high voltage to low transition, a low voltage transition during 1 bit time. A 0, I'm sorry, that was a 0. A 1 is a low to high. So you will see here that we have the bits we want to transmit, and if you look in the middle between the dotted lines, you'll either see a transition from a high to a low for a 0, or a low to a high, for example, the second bit that's shown here. So this is called Manchester coding or Manchester encoding. Okay, moving up one layer to layer 2, the data link layer. Again, from the diagram, the PDU is an Ethernet frame. The purpose is to transmit data between adjacent network nodes. Another way to say that is network nodes that are on the same LAN or in the same network. They all mean the same thing. So transferring data between those nodes is the first purpose. The second purpose is encoding and decoding those Ethernet frames. And then as far as components and devices, at layer 2 we have NIC cards on PCs and we have bridges and switches. So those are considered layer 2 devices. As far as addressing, at this level, and again this is something I will ask quite often, at layer 2 we have MAC addresses. They're 48 bits in length. And the other thing that I will ask a lot is what network or I'm sorry, what address is used to communicate with devices that are on the same network? And the answer is MAC address. So several things on here that I say I harp on, and I always tell my students when I say I harp on them, that means they're probably going to appear on quizzes, homeworks, and tests. The next thing we're going to do is look at what I refer to as a generic Ethernet frame. Again, I will give you 7 boxes and say fill in the fields for these 7 boxes that represent a generic Ethernet frame. One thing to note, depending on where you study, where you read, a lot of times when people draw this, they will only put 6 boxes because they put the first 2 things, the preamble and the start frame delimiter, grouped together. But I think it's very important for explaining how they work that they be split out. Now, the preamble is 7 bytes. I will talk about this. We may come back and see it again. If we do, we'll go through it real quick, but we have some facts. But basically, these 7 bytes are just repeating 10, 10, 10, 10, as far as the bits in these 7 bytes. So that is for synchronization. So when a NIC card sees a signal on the wire, it knows it should be saying 10, 10, 10, and it will use it to synchronize its clock with the clock on the sending computer. And then at some point we get the start frame delimiter, which is 10, 10, 10, 11. And when it sees that 11, it knows that, okay, I am now getting ready to see some other fields that are in the frame. The first thing that will be sent is the 6 bytes, which is 48 bits of the destination MAC address. That will be followed by 6 bytes, which are the source MAC addresses. It will then be followed by a type or length field, which when I'm going through delineating information about these, we'll talk about in a little more detail. Then you have the data, which is 46 to 1500 bytes. And then finally, we have the frame check sequence, which is for error checking, which is 4 bytes. So that's a little bit of information about layer 2 Ethernet frames. The total frame size, not including the preamble and the start frame delimiter, is 64 to 1500. I would ask my students in person class, why doesn't this include the preamble and the start frame delimiter? The reason being is why the destination machine is trying to sync up with the sending machine. It may lose some of the bits in the preamble. It may take it a little while to sync up. So you really don't know where you are until you see that 11 in the start frame delimiter. Okay, so going back and talking about these in a little more detail. The preamble, as I said, was used to synchronize the device clock with the sending device clock. It's 7 bytes of alternating 1s and 0s. Next, we have the start frame delimiter. That is used to signal the start of the frame. And like I said before, it's the byte whose value is 10, 10, 10, 11. The next thing we have is the destination MAC. Again, it is 6 bytes, and it is the MAC address of the destination machine. I've repeated this again, very important. MAC addresses are used for communicating only on the local network. Next we have the source MAC address. So this is the MAC address of the machine that sent the packet. The next field, which I said we'd talk about a little bit more, is the type and length field. If its value is less than 600 in hexadecimal, then that is the length of the data field, telling you how many bytes we have in the data field. If its value is greater than or equal to 600, it is something called the ether type, which indicates what type of packet have we encapsulated. And I want to come back and talk about that term. But first, an example is if we have 800 hex there, that means that our data in this frame is actually an IP version 4 packet. So it's giving you a little insight into what data we have. Now, encapsulation is a very important term. Hopefully you talked about this in your 161 or 160 class. It's basically taking something, wrapping a header and possibly a trailer around it, and creating a new frame or packet or collection of information. So what we did here is we have something, let's say it's an IP version 4 packet. We encapsulated it to make it into an Ethernet frame. So as you're going from a higher level in the OSI model to a lower level, you're wrapping headers and possibly trailers around it to create a new PDU. So we had an IP packet, we wrapped a destination MAC, a source MAC, an ether type before it, and in this case I said that the trailer is optional. We do have a trailer, which is the frame check sequence, the error checking for this Ethernet frame. So the data field is the actual data, sometimes referred to as a payload of the frame. Again, it's 46 to 1500 bytes in length. And the last thing we have is the frame check sequence, as I said, and as you should hopefully know, it's used for error checking. Basically, there's a mathematical calculation on the frame, starting at the beginning of the destination MAC address through the end of the data field that is calculated and then placed in the frame check sequence, which is 32 bits. So we don't include the preamble and start frame delimiter because we really don't know where we are. And of course we don't include the frame check sequence bytes because that's the actual error checking. So it's important to know that this calculation is done on the sender from the start of the destination MAC to the end of the data. That value is put in the frame check sequence. As the destination receives the frame, it performs the exact same calculation, and at the very end it compares what it calculated to the value that's in the frame check sequence. If the frame check sequences do not match, then the frame is discarded. If they do match, then the assumption is going to be that the frame did arrive intact. As far as some protocols that we're going to be talking about at layer 2, probably the first one we talk about is ARP. Its purpose is to map an IP address into a MAC address that we need to communicate with. Probably further down the road, CDP, Cisco Discovery Protocol. That allows Cisco devices to share information amongst themselves. And there may be others we talk about, but that's just a couple of examples. Moving up to layer 3, again, as shown, the PDU is the packet. The purpose is to transfer packets between a source and destination device. It encodes and decodes IP packets because one of the major protocols at this level is IP. At layer 3, the devices that work at layer 3 are routers. Oops, let me back up. Shoot. Okay, very important. You hopefully already have this memorized, but the very last line, addressing, IP version 4 addresses are 32 bits. IP version 6 addresses are 128 bits. If I am talking and I just say IP address, you can either assume that it's irrelevant for me to specify whether it's version 4 or version 6, or if it does matter and I just say IP, then you can assume IP version 4. Okay, some protocols that operate at layer 3. The most common is IP, and the purpose of that protocol is to get packets from their source to destination devices. There is ICMP, Internet Control Message Protocol. This is used to communicate problems with data transmission. There's about 40-some different types of problems that can be transmitted in ICMP. And then also, probably the most common way you hear or learn about ICMP is for ping request, ping reply. So it is used with the ping command. We have IPsec, which encrypts layer 3 data so that our transmission is a little more secure. Okay, next moving up to layer 4, which is the transport layer. The PDU is the segment. Data from our application is broken into segments, and these segments are communicated from a sender and a receiver machine. The purpose is to manage the traffic between those devices and to potentially ensure complete data transfer. Sorry about that. There are some devices, we usually don't talk about this so much. We talk about the devices, but we don't talk about them being considered layer 4 devices. That would be gateways and firewalls. And the addressing that we have at the transport layer is we have IP addresses, but we also have port numbers that we use to communicate. Some protocols. TCP. The first two I'm showing you here are the most common. Transmission Control Protocol. This allows communications between applications, and more importantly, is guaranteed in order delivery of the packets. Another common one is UDP. UDP is User Datagram Protocol. This is best effort delivery. So if there's some transmissions that can tolerate lost packets, packets arriving in incorrect order, that type of thing, you would use UDP. The other thing I tell my students, or if there's no way to correct from an error, then why do you need to know there's an error? So if you're watching a movie and it kind of pixelates, pauses, plays, pixelates even more, pauses, and then plays, there's really no way to recover from that other than rewinding. So it's just going to do the best it can to display all the portions of your movie. So video streaming is going to be UDP. Okay, next layer, session layer. Its PDU is data. Its purpose is to control communications between computers, or the sessions between the computer. Some protocols are RPC, Remote Procedure Protocol, for connecting to or calling other processes that are running on another machine. There's also something called the OSI session layer. This allows users on different machines to create sessions with users on another machine. Layer 6 is the presentation layer. Its PDU is data. Its purpose is to serve as a data translator between applications. So some examples of this are secure socket layer, which is used for dealing with sending encrypted data. Newer TLS is basically considered an improved version. There's something called MIME, Multipurpose Internet Mail Extension. We typically think about this being related to email, but it can be a way to represent non-ASCII data so that you can transfer it over the network without corruption. And another one is XDR, which is a standard for describing and encrypting data. So this, you hear presentation, you think like of the presentation I'm doing right now. It's more how is the data going to be represented and presented within the application. And then finally, layer 7, the application layer. Its PDU is data also. It supports end-user application-to-application communications. Some protocols we have at layer 7, there are zillions of them, but some of the ones that we'll probably talk about in this class is DHCP, Dynamic Host Configuration Protocol, for dynamically configuring settings on network devices. DNS, Domain Name System, for mapping between host names and their matching IP addresses. We will talk about Telnet, primarily for the purpose of turning right around and talking about Secure Shell. Telnet is a way to have an interactive session with a remote machine, but nothing is encrypted. So your user ID, your password, and all your data go across the network in plain text. We've had Telnet turned off at UK for, 15, 20 years at least, in favor of SSH, Secure Shell, which has the same purpose as Telnet, to allow you to remotely log into a machine, but everything is encrypted, so it's more secure. More protocols, FTP for file transfer, a trivial FTP, which is very important in networking. It's kind of a stripped down version of FTP. It does not have any authentication, and there's no error checking in trivial FTP. HTTP, which is the protocol for communicating with a web server, having usually your web browser communicate or a program communicate with a web server. And SMTP, Simple Mail Transfer Protocol, for sending and transferring email. Even more protocols. These are related to email, the next few. We have POP for transferring mail messages. We have IMAP for accessing email and possibly files over the internet. We have MIME again, which allows you to send things like pictures, which are binary in nature, to encode them in such a way that they can be transferred in an email message and reconstructed at the receiving end without any corruption. Simple Network Management Protocol, SNMP. This is sharing information about devices on the network and is often used for network monitoring. So that's the end of this presentation. Hopefully this was all review and refresher for you, but if there's any of this information that maybe you've forgotten since you've had 161 or 160, you might want to, watch this again if you weren't familiar with all those concepts.